Hello, my name is Peter Mccabe, and this is my security policy presentation for GreenPace. In this presentation, I'll walk through the company's core security standards, threat assessments, encryption policies, and best practices that help prevent vulnerabilities during software deployment. At GreenPace, we've implemented a layered security approach called Defense in Depth. This method assumes that attackers will eventually find a way in, so we use multiple layers of protection across every part of the development process. The goal is to reduce the impact of any single point of failure and strengthen the security of our systems from development through production. The threat matrix helps us prioritize the coding standards based on their likelihood and severity. For example, SQL injection and memory protection are high priority because they're both common and severe if exploited. On the other hand, coding standards such as assertions are important, but they don't pose the same immediate risk, so they fall lower in priority. This matrix helps us focus our efforts where they'll have the greatest impact. We've built this policy around 10 secure coding principles. These include validating input data, keeping code simple, and practicing defense in depth, amongst others. Each principle is connected to specific standards. For instance, the principle sanitized data sent to other systems maps to our SQL injection and string correctness standards. This mapping ensures that our policies aren't just theory, they're implemented in actual code. Our 10 coding standards are ranked by threat level. SQL injection, memory protection, and integer overflow are top priorities due to their potential to cause serious damage. Medium priorities include handling strings, exceptions, and race conditions, and lower priority standards like assertions still matter but pose less risk. Prioritizing this way helps developers know what to prioritize. We use encryption in three main ways. At rest, we encrypt all stored data using strong algorithms such as AES-256 to protect it from unauthorized access. In flight, we use secure protocols such as HTTPS to protect data while it's in transit. And in use, we apply controls to protect data in memory or while it's being processed by another application. Each encryption type protects a different part of the data lifecycle. The AAA framework stands for Authentication, Authorization, and Accounting. Authentication ensures only verified users can access the system and encourages strong passwords, multi-factor authentication, and secure login sessions. Authorization limits what each user can do based on their role. Users can access enough in the system to complete their tasks and nothing more, aka least privilege. And accounting tracks users' activity, such as logins, accessing files, and database changes. This layered approach gives us both control and visibility into system access and behavior. To catch vulnerabilities before deployment, we use Visual Studio's C++ unit testing framework. These tests target high-risk areas such as data validation, memory management, and buffer safety. Each unit tests include both good and bad inputs. The first test checks whether getDataSize returns a value that's safe from overflow. The non-compliant version uses an integer, which isn't large enough. The compliant version uses long to prevent overflow. To take it further, we could add static analysis tools to detect unsafe type usage early in the development process. The next unit test involves ensuring that the setAge function properly rejects invalid input, such as negative numbers or values over 130. The non-compliant version allows anything, while the compliant version validates input before using it. This test checks for string handling safety. The non-compliant code causes an overflow of buffer. The compliant version uses strncpy and sets the final character to null. We can take it further by testing with strings of different lengths to make sure truncation and overflows are properly handled. And the last test takes a look at memory management. In the non-compliant version, heap memory is never freed. The compliant version uses a smart pointer to automatically clean up memory. And we can improve testing by simulating exceptions to ensure memory is still freed, even if something goes wrong. This diagram shows how automation supports every phase of the DevSecOps process at GreenPace. In the pre-production stages, such as design and build, we use IDE security plugins and static analysis tools to catch vulnerabilities early. During verify and test, we automate security testing and enforce coding standards. Once we move into production, we use logging, intrusion detection, and performance monitoring to catch live issues. Even after deployment, automation helps us roll back changes and stabilize the system when needed. This continuous loop ensures that security is never an afterthought, but that it's built into every stage of the development process. We rely on a few key tools to automate our security policy. Mccabe is the backbone of our static analysis. It scans our C++ code and flags problems like memory leaks, SQL injection, and unsafe data types. In the IDE, we use plugins that give developers real-time feedback while they code. For testing, we use Visual Studio's C++ unit testing framework to validate secure behavior like data validation and safe memory handling. These tools help catch bugs early and enforce compliance with our standards automatically, reducing the need for manual reviews and speeding up development. Some problems we face right now include some developers not consistently following secure practices. Our testing doesn't fully cover areas like multi-threading or third-party libraries. If we wait to fix these gaps, we risk letting serious bugs like SQL injection slip through. Plus, the cost of fixing bugs is higher after code is deployed. Acting now means better code, fewer bugs, and less technical debt. We can use Mccabe to find issues early and expand unit testing to include edge cases and concurrency. These improvements make audits easier, help us stay compliant, and reduce the need for emergency fixes down the road. We should add policies for using third-party libraries securely and improve our handling of multi-threaded code. Input validation should be required everywhere. We can also expand peer reviews and ensure new developers are trained properly in our secure coding standards. Looking ahead, we should adopt dependency management tools such as OWASP, dependency check, and add secure design reviews early in each project. We also need minimum unit test coverage requirements and continued investment in automation. By continuing to evolve our standards and staying ahead of potential threats, we can keep GreenPace applications secure, efficient, and ready for whatever challenges come next.